Hey everyone, welcome back to the channel. I hope you all are doing pretty well. Let's see today's daily challenge on Leetcode and we will try to solve it together. Maximum distance between a pair of values. You are given two non-increasing zero-indexed integer arrays nums1 and nums2. A pair of indices I comma j where I is the index number of nums1 array and j is the index number of nums2 array, and it is known as a pair of index is known as to be valid if both I less than j and nums1 of I is less than equals to nums2 of j. The distance between the pair is j minus I. Okay, so return the maximum distance between any valid pair. So this is the definition of a valid pair which is given to you, and you need to return the maximum distance of any valid pair I comma j. If there are no valid pairs, you can simply return a zero, and array is non-increasing. So it's already told that the two given arrays to you are descending order, are arranged in descending order. They all are elements will be decreasing order. Okay, either they will be equal or they will decrease. Yeah. So these things are told to you, and you need to find the maximum distance between any valid pair. Okay, so what can be we'll start with the brute force solution and try to optimize this further and further, and let's see how much complexity we can get. And if you try to understand, see what we need to do. We have one array, okay, which we are calling nums1, okay, and whose index we are calling as I. We have another array nums2 whose index we are calling as j, and one obvious brute force solution, and what we know that a valid pair is something like this. Okay, both this and this needs to be valid. Okay, so both this and this needs to be valid for a valid pair. Okay, and you need to find the maximum distance. So one obvious brute force solution should be to iterate through the all i's and j's. So let's say you go through all i's starting from I equals to 0 to let's say n, and then again you go for all the j's starting from j equals to 0 or till m, and you just check that if I less than equals to j, and so basically whatever condition is there, you are just applying it blindly and you write this condition over here, nums I less than equals to nums of j. Then you let's say update some maximum value, so initialize a max as 0 and you can update that as something like this, j minus I. Okay, and at the end you can just simply return this maximum value, and that will be all for the brute force solution. But if you understand it, the time complexity is of the order of O of m in n into m, which will give you an obvious TLE because both are in the order of 1e5. It is already told in the question that both are in the order of 1e5, so definitely that will give you a TLE. Now, if you also notice that we are not using one particular property of this array, that is, they are arranged in the descending order. So, one obvious solution is that you keep iterating through the i's and try to find the optimal j through binary search. Now, how do I get the idea of this binary search? Because the array is arranged in a very specific order, that is ascending or descending order. It is arranged in descending order. We can just reverse it also to get the descending order. So let's say we have this first array, we have this second array. Okay, we can have an I iterating through the first array. Okay, we can have an I iterating through the first array, and for every I will try to find the optimal j. So what do I need to find? So if I have an I which is over here, okay, let's say I is over here and I have some value, I need a value which is just greater than this x, okay, which is just greater than this x in this array. Okay, and we can, let's say, we can reverse this array. So initially it is arranged in ascending or descending order, right? Decreasing order, so you can reverse it to arrange it in increasing order, and then you can apply this lower bound function. Okay, what does lower bound function does? It does nothing but the binary search only, and it works in log n time. That is the beauty of this. So you can in log n time try to find the optimal value of j. Okay, so you can just find this x. So I hope you know how already lower bound function works. If you do not know, you can just quickly Google that out. And it returns an iterator, but you can convert that into an index, obviously. So you get the index where this particular element y, okay, where this y is just greater than this x, okay. And just you now check that if I happens to be less than equals to j, then you can update your maximum in the same way, okay. In the same way, you can just update your maximum value is equal to max of j minus I. And if you notice, what is the time complexity of this? So for all the I you iterated, so O of n must only also be there, and along with this lower bound function, which works in log m time. So n times you use this log m function, so your time complexity will be n log m, and that will be an accepted solution if both are 1e5. Okay, but let's try to see what is the percentage bits and all we get for this. So we will just try to have n as this and m as nums2 dot size. Okay, and I will try to find the optimal j every time, but first I need to iterate through this array nums1. Okay, after I have this array, so let's say x, I get the value x, which is nothing but nums uh, 1 of I. Okay, so I need to find a value in nums2 which is just greater than nums1, right? So which value that index is present, in which index number that value is present. Before all this, I will just try to reverse this nums2 because of the working of upper bound function, lower bound function. So nums2 dot end. Okay. So after I have this, I can simply write the upper bound function, which will be nums2 dot begin, nums2 dot end, as we need to find this function. And as you know, this upper bound function returns an iterator which is pointing to the particular element. So in order to get the index, I need to do nums2 dot begin. This whole thing will give me the index number at which a particular value is just greater than this x. Okay, just greater than or equal to this x. That is what this upper bound function does. Yeah, now once we have this index number, okay, we can call it j, because that is what, right? That is what it is. So I can try to initialize one value maximum equals to 0, and see, once we have already got this j, right, we need to ensure that this upper bound function actually returns some value. If it does not return, it will point to nums dot end, and this j will be n. So, if j is equals to n, okay, then you can continue with. Okay, I do not need to update any values if j is n, because uh, we did not even find any particular value. So what did we update? What do we need to update? J cannot be n. Okay, the index number must lie between 0 to n minus 1. So what is this n? This is nothing but m. Okay, this is nothing but this m. Uh, yeah, after this, if j is not m, we have a particular value, and if we check that if I happens to be less than or equals to j, see, there are two conditions. Nums1 of I less than or equals to nums2 of j, that we already got because we found the optimal j. Another condition is just I less than or equals to j. We just check that if that is also valid along with this condition, then we can simply update our maximum. So max of j minus I. Okay, and you can just return this max for. Okay, and if you try to run this, let's see. Okay, so as of now we are getting some errors, so let's try to see what is our mistake over here. So what we do, we take a value nums1, we iterate through all the nums I, and upper bound, upper not upper bound, okay, sorry, lower bound, right? because greater than or equal to thing we are finding. Okay, so yeah, we did lower bound and we want to search on this nums2, okay, which is nums2 dot begin, nums2 dot end, and we also make sure that it is arranged in an ascending order. So once we have it, once we have this value of x, we have this j. Now if j is equals to this nums2 dot size, it means that we should not update this. Otherwise, if I is less than equals to j, we can update our value. You see one thing, this is not the actual value of j, right? Because we have reversed this array nums2, okay? So let's say if currently, so see, in the second array, if currently j was pointing to this element, okay, then in this is the reversed array. It should actual j is actually the reflected value, right? So if j was pointing to the first element right now, then it is actually pointing to the last element. So this is kind of the case. If it is pointing to the last element, it should be pointing to the first element because we have reversed the array, right? So in order to actually correct this value of a, we need to do something, and that's where this m minus 1 minus j, we can just find the reflected value of j and we can try to run this, okay? So you see, we do get accepted. If you try to submit it for all the cases, I hope it will work. It should work. Let's see. Yeah, it does work, but you see the time complexity is not very much optimal. So we will try to optimize it even further to even something like O of n, okay, or O of m plus n. So that will be even more optimal. So let's see. Uh, See, since these elements are arranged in a particular order, we can try to use a two pointer, okay? So since both are arranged right, that's why we can try to use two pointers. Let's I and j be both initialized to 0, okay? Now for every I, as we were doing in this in my previous method, it is very similar to that only. For every I will try to find the optimal j. So I will try to find the j. I will keep increasing till I get a value where nums of j. See what I need. What do I need actually? I will need a value where nums where uh, this nums of j is just greater than or equals to this nums of I. Okay, I need such a kind of value. Why? Because I want to go as far as possible, and it is both are in decreasing order, right? So I will try to increase and increase the value of j till I find somewhere where the nums of j happens to be uh, less than the nums of I. Okay, then and from this position, if I do j minus minus, okay, from this position, see, we want this criteria, so we keep iterating till we have violated that criteria and just move one step back, then we will get the optimal value. Okay, so once we get that optimal value, we can just update this j. And if you think little bit, even when this I will, you might be thinking that, hey, we were finding in binary search which was taking log of m, right? Now you are telling to take steps and find, it will take m, right? But that is not the case. For every n, it will not take m, because once you increase the value of I, okay, once you go to I plus 1, see, you decrease the number, right? Because it is in decreasing order, so your new number at I equals to 1 is decreased right now. And also, if you try to find a particular value of j, you will not need to go back, because you do not need any increased value, because this value is only decreased and you want a value which is even less than this. Okay, I hope you do understand, and that's why you always need to keep incrementing j. Always keep incrementing j, and that is why your solution now will be n plus m, O of n plus m. Okay, it's a simple linear solution it will be, and this is the standard two-pointer method. You have done it previously, a similar kinds of problem for two-pointer. I hope this will not be any issue for you. So, and I hope even if you have do not done, uh, did understand what do I mean by this solution. So it is the same thing I will try to do, but instead of a binary search right now, I will try to mm, iterate the value of j, and I will never try to decrease j. So while let's say j less than m, okay, I do not want j to exceed its bound. That is always true, and nums of I is less than equals to nums of j. Okay, while this is true, you can keep incrementing j, and we make sure that if it is incremented, so you see, once this happens, it means that uh, j has just exceeded, j has just violated this criteria. Now we do not actually want to violate this criteria, but we also want to find the value of j which is just greater than this nums of I. So we do j minus minus. We move one step back. But what if this never updates? Then every time this will move one step back. So it might give you a negative index also. So I'll just check if j is greater than 0, then only try to move it one step back. Okay. And every time after this happens, I can just update this j minus I. That will be all. And if I try to return this max, you see, we have a simple and short solution. You can try to run it. Okay, so 1 and 2, nums 1, nums 2 is there. Yeah, let's try to run and see. Yeah, we did get accepted. Now, if we try to submit this solution, I hope it will just work fine without any issues. Yeah, you see, it did just work perfectly fine. When I submitted this, this gave me a perfectly 100% runtime bits. It is now still giving me a decent. But yeah, that is all, I guess. That is all for this video. And this solution, this is definitely a better and a more optimal one. And I hope you were able to understand all the three methods, and it should be clear to you. That's all for this video. If you have any doubt, definitely ask me in the comment section. Yeah, I will meet you in the next video. Till then, thanks a lot.